There's one final thing that we were going to talk about, but I needed to finish the lecture. It's also related to the compiler optimizations. Sometimes the C51, the Keil C51 compiler does not do this, but sometimes your compilers will optimize stupid lines. So one of the examples that we had, okay, so how are we gonna, so sometimes if you're, let's just grab a whiteboard until Keil is open. Actually, Keil is open. Right, so desktop one, can you see my desktop right now?
Yes.
Okay, so Keil is a little bit smarter than that. It's smart in the sense that it's dumb. And if I say, for example, put a line that says accumulator equals accumulator, right? Your standard GCC, even with the standard optimization flags, would simply see this line and it would be like, right, this is stupid, I'm not doing this, it has no effect, and it would destroy it. It would not compile it. It would not be linked. Whereas Keil is a little bit smarter than that, and it assumes that every time you do a stupid thing like this, it usually has it assumes that you have a reason. Right, sorry. Missing comma before serial buffer index. What are you talking about? I haven't touched this code since whenever. Oh, crap, I know. And then when we start the debugger, and when we look at the disassembly, we can actually see somewhere around here, right? If I may take your attention to this line, accumulator equals accumulator. Actually, we can already see that even Keil did not compile this line. You see that this assembly shows no line. Can you see that? Do you see that there is no assembly line for this instruction?
Yes.
Yes.
Okay. So the thing is, even the Keil compiler will do some sort of optimizations, and one of these things is, for example, again, sometimes you will have a local variable like counter, right? And then perhaps you will have your ISR. Great. And then perhaps you will have a pointer like this. And yeah, we've said that this is all for practice, but let's start with that. So perhaps we did something like my pointer equals and counter. Right, this is C99. Now my pointer has, as soon as my main starts working, my pointer has the address of the variable counter. And then next thing we know, say for example, we inside our ISR, what we do is something like this. We increment, we dereference my pointer, and we increment the variable, right? Something you could potentially do, why not? But in the end, you have your counter plus plus here, and let's say that instead we now have a stupid line like this, ACC equals counter here. And then we also have a copy of In fact, let's not worry about that. So we just have counter here. And inside the main, we only have counter here. It's only initialized, which if you ask the main function, counter is only initialized. And then counter is only printed if you ask the main. So a smart compiler would just, instead of compiling an entire printf line here, it would instead just put a constant in here. Because why not? As far as the compiler sees, main does not change the counter at all. And it's a local variable. As far as the C compiler sees, counter is not going to change. But here's the thing. You just gave its address. You just gave its address to a pointer. And in which case that pointer is used to dereference the counter variable and then to increment it as well. So it is actually going to change. But the compiler might be dumb. Well, compiler might not. Compiler is not that smart to be able to trace the pointers. Right, code size exceeded. Amazing. I hate myself. Unfortunately, I won't be able to demonstrate, but I think you get the point. This could have been compiled as a 0. And to be able to, depending on the compiler, there is a keyword to prevent that. Have you ever used the volatile keyword for anything in CS201 or 202, or have you heard about the volatile keyword?
I don't think we use it.
I used it in another system to get debugging information.
For volatile? With volatile?
Yeah, well, not specifically in a system, but just on a program.
Okay, well, interesting. Just 1 second, by the way, since there's no one in class, there's nothing stopping me from using my native screen resolution. Oh, thank God. Right, so the volatile keyword, it does something very, very simple, assuming that you can see the PDF. The volatile keyword tells the compiler to turn off optimizations about that variable. So let's look at the code here. And if I just define this volatile, well, we couldn't see it, but you can at least see that it doesn't give any warnings. It tells the compiler to turn off any optimizations regarding this variable. So if there's a line and the compiler is thinking, oh, I can optimize this, it just tells it, don't do it. It doesn't tell anything more than that, but it's good because the C compiler, like we've said, regardless of what compiler you use, is not able to understand when an ISR kicks in and that variable may change. And even though, to make things even worse, what I've just done is that I actually modify that variable by using its address, by using its reference. So there's no way any compiler will be able to understand what I've just done. We could even do even worse things. We could literally write the address of a variable, which is, like I said, awful practice. Don't do it. Like, honestly, don't do it at all. But if I declare my variable as volatile, it will turn off the optimizations about it. It will not destroy any lines. It will not reorder any lines. So everything will be as is regarding that variable. So that's a good thing. So any questions until this point? Anything about interrupts? Anything about disabling and re-enabling or restoring interrupts?
Hocam, can I ask something?
Yes, please.
I'm not sure if it's discussed. It may be trivial, but can we force interrupt in any point of the code?
Yes, you can. So in the last lecture, actually, we were discussing that, and there wasn't too much time, so I didn't necessarily bother with it. So give me just 1 minute, and hopefully I can actually show you an example. So while I'm preparing that, I'll actually also explain what's happening. So what it erases an interrupt, right? So what causes the CPU to interrupt is a couple of bits, literally a couple of bits here and there defined in some registers. If you manually write a 1 to those registers, then you will be able to raise an interrupt just like that. So one of the examples that I'm going to have right now is just a second. So normally, for example, for a serial port, if the RI flag becomes 1, if you receive a character, or the TI character becomes 1 if you finish transmitting a character. Alternatively, RI will become 1 if you receive, TI will become 1 if you finish transmitting. And when these flags become 1, and if the serial port interrupt is enabled, then it will be these flags which will actually make the CPU jump into the ISR. That means if somewhere within my code, say for example here, then I will be able to raise and interrupt myself. You can see my screen, right?
Yes.
So if I take your attention to line 103, I'm going to set the RI to 1 and I don't know, hope that it will raise and interrupt just like that. I know for a fact that it will compile. So I'm just going to do line by line. So right now I'm just about to execute RI equals 1. What I expect to happen is that I'm going to jump into the ISR after this. And we did. It wasn't that obvious, but we immediately jumped into the ISR like that. Can you see that? Were you guys able to observe that?
I see that. Okay.
Sorry, could you say that again?
Yeah, I said I see that.
Yeah. So this may not be, like, to be perfectly honest with you, this may not be applicable to all interrupts, but I know that this worked for this one. And then the program continues just like that. Okay. But it should be possible, because this way, the microcontroller also allows us to test our ISRs at random points as well. Let's not say random, but at arbitrary points as well. So say, for example, if you would like to test what happens if you receive a receive interrupt, you could inject some code in here to allow you to test your code, test what happens if you receive an interrupt here. Or you can grab it and you can put it here, for example, and see what happens if it happens there, and so on and so on. Of course, this is some sort of like a soft debugging technique. Alternatively, what you can also try is that if you have a good simulator or an emulator or the actual hardware, which would be my preference, you can start debugging it. And you could literally run it line by line. Say, for example, we'll just come here, and then I'm about to reset the serial buffer or something like that, or whatever. And then I could literally, because the Keil simulator allows that, I could stop right here, and then I could press a letter. Even though it seemed like nothing happened, I know for a fact that something happened. Actually, nothing happened because I had not apparently enabled the interrupts. But as soon as I enable the interrupts, I know what's going to happen. Or, right, there we go. And then I immediately jumped into the serial ASR. And the serial ASR, I know what it's going to do. It's going to reprint my TI, reprint the character that I had, and send it back to the serial port. As you can see here, okay, sorry, right. If I may take your attention to UART1 screen on the right-hand bottom side of the screen, you see that it now writes ties off instead of size off. Well, surprise, surprise, T was the letter that I pressed. Right.